Diving. I'm going to investigate the motion of a diver doing something like this, jumping up, then dropping into the pool. Firstly, the free body force diagram. Well, we can draw the diver something like this. There's no need to draw an actual person. And the only force acting on the diver is their weight acting down. This is assuming that it's a fairly short dive and we can ignore air resistance. This will usually be the case at A level. First we'll look at the motion graphically. Here's a displacement time graph. If we take the diving board as zero displacement, the diver initially goes above and then below the diving board, so we need to show positive and negative displacement on the graph. It doesn't matter which direction we take as positive, as long as we're consistent throughout the question. I've decided to take up as positive, so the diver initially went above, then below the diving board, giving a line something like this. Now the velocity time graph. Well, the diver started going upwards and we're taking up as positive, so they would start with a positive velocity. This quickly reduced to zero before increasing in the negative direction. As the only force on the diver is the weight, the acceleration due to gravity would be constant, giving a straight line, something like this. If we now plot an acceleration against time graph, it would show a constant acceleration of minus 9.81 meters per second squared. The minus sign is because we've taken up as positive. Now to look at how the equations of motion apply in a situation like this. Well, here are the equations of motion, but the acceleration for a diver is g, the acceleration due to gravity. So replacing a in these equations with g, we get this set of equations. V equals u plus gt, s equals u plus v over 2 times t is unaffected, v squared equals u squared plus 2gs, and s equals ut plus a half gt squared. Let's look at a problem. A diver on the 10-meter board jumps up with an initial velocity of 3 meters per second. Find his maximum height above the board, his velocity on entering the water, and the time taken to hit the water. Well, this problem is best dealt with in two parts. At first I'll look at going up, for which I'll gather S, U, V, G and T. S, the upwards displacement, is what we want to find, so I put a question mark. U, the upwards velocity we're given in the question of 3 meters per second. V, the final upwards velocity. At maximum height this will be 0 meters per second. G acts downwards and so is minus 9.81 meters per second squared, as we're still taking up as positive. And T is not necessary, so I've left it blank. We're looking for an equation which contains S and does not contain T. So we can use V squared equals U squared plus 2GS. Rearranging the equation to make S the subject, we get V squared minus U squared over TG equals S. Putting the numbers in, this is 0 squared minus 3 squared over 2 times minus 9.81, giving an upwards displacement of 0.46 meters. About half a meter. This seems reasonable. Now for going down we can use the whole of the journey, and so again I've got SUVGT. S, in this case the downwards displacement, will eventually be minus 10 meters. U is still plus 3 meters per second. He still starts going up. V, in this case we want to find. G is still minus 9.81 meters per second squared, and this time we need to find T, so I've given a question mark. Initially we're expected to find the velocity on entering the water, V here, so I want an equation which contains V and does not contain T. Again, I'm going to use v squared equals u squared plus 2gs. Putting in the numbers, that is 3 squared plus 2 times minus 9.81 times minus 10, giving v squared of 205.2 meters squared seconds to the minus 2. Square rooting this gives v minus 14.3 meters per second, minus as he's going down. And finally, to find the time taken to hit the water, we can now use v equals u plus gt. Rearranging gives v minus u over g equals t that we want to find. Putting in the numbers, v was minus 14.3 minus u of 3 over g of minus 9.81 gives a time to hit the water of 1.76 seconds. Again, a quick check, this seems to be a reasonable figure.